Good morning, everyone. My name is Yujie. Today, I will be presenting our work of computational storage, CompoundFS, compounding I/O operations in firmware file systems. This work is done in collaboration with Jian, Zhang, and Sudarsun Kannan at Rutgers University. Modern SSDs are powerful compared with their ancestors more than 10 years ago. In addition to lower prices and higher storage capacities, modern SSDs are equipped with more powerful CPUs, larger in-storage DRAM with only tens of microseconds latency. Now the I/O bottleneck has shifted from hardware to software. When an application wants to access a file on the storage, it needs to trap into OS kernel, and there are multiple layers in OS kernel I/O subsystem. Three types of software overheads dominates: kernel trap, data copy, and OS overheads. For write system call, if that is on a ext4 file system, it needs to go through multiple layers from VFS to device driver. For byte addressable NVM and special file systems like PMFS, it will go direct to the storage. The overall software latency for I/O system call is around 1 to 4 microseconds, which is no more negligible for ultra-fast storage. To reduce software overheads, prior works have aimed to implement and develop direct file system access by passing OS kernel. Strata is a user-level file system. Each application has a user file system library managing data plane operations, and a trusted FS server that is responsible for updating metadata. SplitFS, an NVM user space file system, moves data plane operations to user space via load and store instructions and leaves control plane operations in kernel DEX file system like traditional file system. DevFS takes a radical approach that offloads the entire file system into storage, and the firmware-FS is responsible for updating both data plane and control plane operations. There are several limitations of current solutions. First, DirectFS design do not reduce boundary crossing. Strata needs boundary crossing between FSLib and FS server. SplitFS needs kernel trap for control plane operations like open. It needs to gather memory map staging files, which might be time-consuming. DevFS, while it bypasses OS entirely, it suffers from high PCIe latency for every operation. Second, DirectFS design do not efficiently reduce data copy. For data plane operation, one or more data copies is needed between applications and storage stack. Third, DirectFS design do not exploit the increasing capability of in-storage computation. To analyze what are the exact software overhead, we provide an I/O-intensive application. We emulate persistent memory on DRAM like prior work. We select two direct file systems, ext4 DEX, which is ext4 on byte addressable storage by passing page cache, and SplitFS, direct access file system by passing kernel for data plane operations. We select well-known level DB persistent key value store as our target application and dbbench random read and write benchmarks. Here's our result of our analysis. We list 7 top software overheads: data allocation, data copy, cross boundaries, file system updates, file system logs, data allocation and data copy in user space, and finally the CRC, which is checksum calculation in user space. Here are 3 takeaways. Level DB spends significant amount of time in OS storage stack, and 15% of time spent on data copy between app and OS, and 20% of time is spent on app level crash consistency. Level DB using checksum to reduce fsync. To overcome such limitations, we propose CompoundFS. CompoundFS combines multiple file system I/O operations into one and offload I/O pre- and post-processing to storage-level CPUs, and also bypass OS kernels, provide direct access. We observed that multiple I/O operations are consecutive and tightly coupled along the application code path. For example, write system call is often issued after read for the same file, so we compound read and write operation to write after read. Hence, it reduces boundary crossing between host and storage. In addition to tightly coupled and consecutive I/O operations, there are also computation that's related to I/O. For example, in level DB, after writing the data block, it calculates the checksum of the block and also write the checksum. We compound checksum after write to write and checksum compound operation, and offload the checksum calculation to storage CPUs and persist both data and checksum. Hence, it reduced data movement cost across boundaries. Like prior works, CompoundFS adopts firmware-level file system design to provide true direct access. Here's an example of I/O-only compound operation, read, modify, write. In a traditional file system path, an application needs to trap into the kernel, read the data and copy to the user space, modify the data, and then write the data block to the storage. Hence, two system calls and two data copies are incurred. In CompoundFS, all the application need to do is to issue a read, modify, write compound operation, and the storage FS performs compound operation. The second example is compound operation with computation, write and checksum. In a traditional file system path, it first needs to write the data, trap into the kernel, calculate the checksum, and finally write the checksum. Hence, it will incur at most two system calls plus two data copy overheads. In contrast, CompoundFS only need to issue the write and checksum compound operation with only one data copy overhead, and the storage FS handles checksum calculation and persists both data and checksum. Here's a high-level architecture of CompoundFS. Each application has a user library FS converting I/O system calls to compound operations, and per inode I/O queues and data buffer. The storage FS runs in storage device with device CPU cores, and the I/O request processing threads runs on top of these device CPU cores. CompoundFS has similar in-storage and on-disk file system layout and structures to traditional file system, and the journaling mechanism is also similar. Storage FS also maintains a credential table that exchanges permission and information between host OS and storage FS to guarantee security. For example, when application thread 1 issues the open, the storage FS will process this request, and later thread 2 issues a read and modify write compound operation. Similarly, the storage FS is responsible for processing this compound I/O operation. The third operation is a write and checksum compound operation. It will add to the I/O queue, and the I/O request processing threads will perform CLC calculation and persist both data and checksum. The fourth operation is a regular read operation. The flow is similar. To implement CompoundFS prototype, we extend PMFS with a command-based architecture via I/O control system call carries arguments for each I/O operation. I/O control can avoid VFS overhead for control plane operations. However, for data plane operations, in order to avoid system call overhead. In addition to VFS overhead, we design a shared command buffer between user library FS and storage FS. User library FS adds requests to command buffer, and storage FS process requests from the buffer. To realize CompoundFS, there are several challenges. The first one is, how could we design a crash consistency model for compound IO operations? Our current solution is all or nothing model. In this model, an entire compound operation is a transaction. Partially completed operation cannot be recovered. For example, in a write and checksum compound operation, if a crash happens in between, only the data is persisted, but the checksum is not yet. When we recover the compound operation, the persisted data block is not able to recover because the entire write and checksum compound operation is a transaction. Our ongoing work is to exploit an all or nothing model, which provides more fine-grained journaling and partially recovery, but this might be more complex. To study the efficiency of CompoundFS, we evaluate CompoundFS with 2 microbenchmarks and a real-world application. Our evaluation goal includes effectiveness to reduce boundary crossing, effectiveness to reduce data copy, and ability to exploit compute capability of modern storage. We run CompoundFS on a dual-socket 64-core Xeon processor with 512GB Intel Optane NVM as our storage. Due to the lack of commercially available storage raw device, we emulate firmware-level file system like prior works. We reserve device threads handling IO requests, add PCIe latency for every request, and reduce CPU frequency for device CPU. We compare CompoundFS with 3 state-of-the-art file systems, ext4dex, SplitFS, and DevFS. We first evaluate them on 2 microbenchmarks. The first is read-modify-write benchmark that read the block, modify the data, and write it back on a 16GB large file and measure the throughput. We study the performance of 2 block size configurations, 256 byte and 4K byte. As is shown in the figure, as block size increases, throughput increases because the amount of system call and data copy overhead is reduced. SplitFS and DevFS is able to show higher throughput than ext4dex due to the design of DirectFS. CompoundFS reduces unnecessary data copy and system call overhead by compounding IO operations, and it shows up to 2.1x gains over ext4dex. The second benchmark is write and checksum that write the data block, calculate the checksum of the data, and then write the checksum. Similar to read and modify write benchmark, CompoundFS could achieve high throughput compared with state-of-the-art file systems. Even with slow CPUs, CompoundFS can still provide gains for in-storage computation. We next evaluate CompoundFS with LevelDB on DBbench random read and random write benchmarks. For random read benchmark, it measures the latency of each operation. As is shown in the figure, CompoundFS is able to show lower latency compared with ext4dex. For random write benchmark, it measures the throughput. CompoundFS could achieve up to 1.75x compared with ext4dex. That is because CompoundFS reduces system call data copy overheads by compounding multiple IO operations and offloading IO-related operations like checksum to the storage. To conclude today's talk, storage hardware is moving to microsecond era. Software overhead now matters, and storage computational capability is powerful. As shown in our work, CompoundFS combines multiple IO operations and reduces multiple boundary crossing and data copy overhead, and takes advantage of in-storage compute resources. Our ongoing work will focus on, first, design fine-grained crash consistency mechanism, and second, implement efficient I/O scheduler for managing computation in storage. Thanks for your attention.